Here we're going to run through all the different things you can do with surds, quite a few examples, going to go through them all quite quickly. Do feel free to pause it and look at parts again if anything isn't clear. So here we've got two surds being multiplied together, root 5 multiplied by root 5. So when you're multiplying surds, you can multiply the numbers inside and leave those in a square root. So you could get this as the answer. 5 multiplied by 5 is 25, so therefore root 5 times root 5 is root 25. But also, of course, the square root of 25 is just 5. You could have got there more quickly by realising that if you're squaring a square root, remember squaring means just multiplying by itself, that's going to undo the square root. So another way of seeing this question would be root 5 squared. And because squaring and square rooting are opposites, they're just going to undo each other and you get 5. It's a very important rule for surds. When you're adding surds though, what you are not allowed to do is this. That's wrong. Root 3 add root 3 is not root 6. Instead, you have to treat the surds kind of like algebraic terms. So there's one root 3 here, it's another root 3 there. What you've got in total is 2 root 3's. Same thing here. Here's 4 root 3's, add 7 root 3's. So you're just going to collect up all the root 3's, and in this case we've got 11 of them. Okay, so you can go backwards with the same technique we were just looking at. Root 20 could be broken down into two numbers that multiply to make 20, two of its factors. So in this case, there's probably quite a few examples. We could put 10 and 2, I guess 20 and 1. Always try and aim for finding a square number for one of these so that you can then simplify that. So root 20 could be written as 4 and 5, root 4 times root 5. Now this is good because we can actually do root 4, which is just 2, and then just squeeze this in here. The root 5 will just stay as it is because you can't do that one. Therefore, the answer would be 2, normal 2, root 5, because that is just 2. So root 4 is not actually a surd. A surd is when you can't actually calculate it and it has to stay in the square root. Root 4, even though, yes, it has a square root, it's not called a surd because you can actually turn it into a normal 2. So you see a more complicated example of the same technique with this. We're trying to add root 200 to 3 lots of root 32. Now you can't do that because you can't just add surds, but you can break them both down until you get the same surd, and then you can add them. So root 200, again, I'm looking for square numbers, so I'm going to spot straight away that I could go for a root 100 times root 2. Over here is the same thing. Now be careful with this. 3 is not in a square root, so that's going to stay there. And remember, there's a multiplication sign here, really, 3 times root 32. So I'm going to write these all as a multiplication now. 32 can be broken into 16 and 2. Again, I'm picking 16 because it's a square number. I'll do all the actual square rooting now. So 100 can become 10. And then that's going to be times by root 2. That can't be broken down. Add 3 lots of, well, that's going to be 4. Times root 2. So it's not root 4. Root 16 is just a normal 4. So now we've got 10 root 2's plus, well, that's going to be 12 root 2's, and now we can add these together for 22 root 2's. This question here is one where it's asking you to factorize these two terms. Now, factorize means put into brackets. You have to find a common factor, a number that goes into both of the terms. Well, clearly at first there's nothing we can see here. This is a number 9, this is a root 54, but always a surd questions, if you start breaking the surd down, hopefully something's going to come out of there that you can then use. So let's do that. Root 54, there's quite a few different options, but I know that it's in the 9 times table, and 9 is a square number, so I'm going to go for that one. And that's going to be root 9 times root 6, and that 9 is just going to stay there. Do the root 9, so that's actually going to be 3 times root 6. That 9 is still there. Now here's the two terms. We actually do have something that goes into both of these. 9 and 3 root 6. Well, 3 goes into both of these terms. So I'm going to put 3 on the outside of the bracket. What's going to have to go here to make this 9 come out if we expand it? 3 times 3. What's going to have to go here to make 3 root 6 come out if we expand it? Well, positive root 6. And if you just check it by expanding it, you'll see you get the same thing. So 3 times 3 is 9. 3 times root 6 is 3 root 6. So therefore, that is correct. Probably the most common thing you're asked to do with surds is rationalise the denominator. So the denominator is the bottom part of the fraction and it's not allowed to be a surd, so we want to get rid of that. The top can be, that's fine, just not the bottom. So the technique is to multiply the fraction top and bottom by something that's going to get rid of this root 10. We saw in the first example, if you multiply something in a surd by itself, it's going to get rid of the square root. So we're going to multiply by root 10, but we've got to do the top as well, otherwise we've just completely changed the value of the fraction, and we're not trying to do that, we're just trying to rearrange the way it's written. So we're going to do the same to the top and bottom, therefore it will be an equivalent fraction, but it's not going to have a surd on the bottom now, it's going to have a normal 10, and on the top, 1 times root 10 is just root 10. So that's the answer, it's a rationalised denominator. Same thing here, there's a root 10 on the bottom. A 5 is on the top now, but that does not affect the calculation we're going to do. We're still going to do times root 10 on the top and bottom. And we're still going to get 10 here, but 5 times root 10 is 5 root 10, not root 50. Remember, that's not a square root, so you can't combine them in a square root. Just going to be 5 times root 10, 5 root 10. Now this one actually can be simplified a little bit, because if you imagine that root 10 wasn't there and you just had 5 over 10, you could divide the top and the bottom by 5 and simplify the fraction. Well, you can still do that even though the root 10 is there. Now dividing by 2 is only going to affect, dividing by 5 is only going to affect the 5. So if we do that, we're going to get 1, so I'm not going to bother writing, over 2. So we divided the top and the bottom by 5, and we've got that simplified version there. Getting a bit more difficult is when you have to expand a bracket with surds, in this case double brackets. So you know how to do that already, I'm sure, but with surds it's easy to make a little mistake. So we'll try and go through this really carefully. Root 7 times 4, so that's going to be 4 root 7. Then root 7 times root 7, that's just 7. 1 times 4, that's 4. 1 times root 7, that's root 7. So this is expanded. We can do some simplification now. 4 root 7s and 1 root 7, that's 5 root 7s, and then the numbers themselves, 7 and 4, is 11. So that is our expanded bracket. And the last thing, rationalise denominators when you've got a denominator that looks like this. So problem is here, we can't just multiply by root 6, because if we did that, probably worth seeing what happens if you do that. Multiply by root 6 on the top and bottom. Yeah, it's not really a big problem for the top. We're just going to get 4 root 6. But when we do this, we have to remember that there's really a bracket around this. So we're doing root 6 times 1 and root 6 times root 6. So what you get is 1 times root 6 is root 6. And then, yes, you get root 6 times root 6, which is just 6. But you've still got a surd, because you had to multiply this normal number as well. So that hasn't got rid of the surd from the denominator. So we haven't actually done the question we were asked to do. In that case, we have to think of a different method for getting rid of this surd here, and we do that by multiplying by something called the conjugate, which is exactly the same thing but with the sign reverse. So in this case it's 1 plus root 6. We're going to multiply by 1 subtract root 6, and do think about these as being in brackets. So it's 1 subtract root 6, and of course you do the same thing on the top. Okay, so we're expanding this bracket basically. Now that's going to require quite a bit of work. But let's see if we can do it. So 1 times 1. Try and do the lines in here. It gets a bit messier when you do that, but we'll see. 1 times 1 is 1. 1 times negative root 6 is negative root 6. Root 6 times 1 is positive root 6. And this is what you want. You can see here we've got negative root 6, positive root 6. Those two are going to combine together and cancel out, which is what you want to happen. And then root 6 times negative root 6 is negative 6. Be careful with that. A positive times a negative, still a negative, even though surds are involved. That rule doesn't change. On the top, a bit easier. So 4 times 1 and 4 times negative root 6. So it'd be 4 and then negative 4 root 6. If we simplify this, on the top, can't really do anything there. So let's write that as that. On the bottom, well, these two are going to cancel out, and then you've got 1 subtract 6, which is minus 5. And in this case, that's about all you can do. Sometimes you've got to look for, can you divide everything by a certain number? Can you divide them all by 2? But we've got 5 in the bottom here, we've got 4s here, so that's not going to work in this case. So probably just leave it like that, but do look out for any possible simplifications. Okay, try the questions.